In this lesson, we're going to look at waves, which are closely connected to simple harmonic oscillators. So, periodic motion is any motion that repeats itself. We've already covered this ground. Some examples are listed there. We've already talked about those. Periodic motion doesn't have to be simple. You can have fairly complicated periodic motion. So if you take a look at this graph here, maybe a bored dog is wandering around. So this motion is actually periodic, but finding the period's a little bit tricky. So you have to ask yourself, if the dog starts walking at 0 and goes up to 2 meters, and then he goes back to 1.25, and then he goes to the right and to the left and to the right and to the left, it's actually not until this point here that the dog begins to repeat its motion. So you can imagine if you were going to sort of continue this trend, you would have to take this entire section here all the way up to 6.3 seconds or so and copy and paste it in order to get the matching graph over again. So this is what is called periodic motion, but it's complicated. So we're going to stick to simple periodic motion. Okay? So simple harmonic motion is a special type of periodic motion. It's when we have this linear restoring force, which we talked a little bit about. When a spring is pulled from equilibrium, it tries to pull back and tries to keep it at equilibrium, and if you pull it down, it bounces. Okay? So that's what we call a simple harmonic oscillator. And when you look at the position versus time graph for a simple harmonic oscillator, it's a very nice, smooth sine wave. So linear restoring forces are what cause harmonic motion. We're going to skip that. When you have a linear restoring force, like in the case of a mass on a spring, or a guitar string, or a piano string, or any taut wire or cable, and you displace it from equilibrium, it vibrates, it oscillates, and it's called simple harmonic motion. And we call it simple harmonic motion because sines and cosines are what mathematicians call the harmonic functions. So we call it simple harmonic motion. So quickly review here. The period is the time it takes for the motion to repeat itself. We use t as the variable, and we measure it in seconds. The amplitude is how far it is displaced from equilibrium. So in the case of a pendulum, it's how big the swing is. In the case of a mass on a spring, it's how far you pull it down before you let it go. The amplitude is just a distance. It's measured in meters, and we use A. And we're not going to do any calculations with the amplitude. The frequency is similar to the period. The period tells us the time it takes for the motion to repeat itself, or how long it takes for a cycle to complete. The frequency tells us how many cycles are completed in a second. So remember, frequency is F, and it's in cycles per second. So here's a quick review problem. If I have a mass bouncing on a spring, and it completes 5 cycles in 8 seconds, what is the frequency and what is the period? So if I take 8 and I divide it by 5, and I keep my units on there, I'll get 8 seconds divided by 5 cycles, and that will give me 1.6, and my units will be seconds per cycle. So this is a time. It's 1.6 seconds. The seconds are in the numerator, and so if it's a time, it's the period. On the other hand, if I take the 5 and I divide it by the 8, I get cycles per second. So that's 0.625, and since that's cycles per second, since cycles in the numerator, that's a frequency. Okay, so if you have a period, it's a time. If you have a frequency, it's the number of cycles per second. So in this case, 0.625 cycles per second is 0.625 hertz. All right, so other examples of simple harmonic motion that we're going to look at, atomic vibrations are a good example. And you've probably covered that in chemistry a little bit, but light is a good example of simple harmonic motion, and sound is too, and we're actually going to study sound in this unit. And then we'll study electricity in the next unit, and for example, AC electricity, the alternating current, it's a current that varies sinusoidally, so it follows the same pattern as the simple harmonic oscillators. So today the topic is waves. So the question is, what exactly is a wave? So what we're going to do is look at a little simulator here. Okay, so what I've got is I've got a string, And I've got a whole bunch of, so you can imagine these are little tiny masses all connected by springs. And they're stretched taut and they go on forever. They go on out the window to the right. If I make a disturbance on the left-hand side, that disturbance propagates down the string or the spring. And that is what we call a wave. Okay? So a wave is a disturbance which can propagate through a medium. And we'll unpack that in a second. So a wave is a disturbance in a medium. What is transmitted is energy, not matter. So if you go back to here, you look at this little mass right here. After I send a wave, that mass is still right there. The mass was not transferred. The energy propagated down the spring, but the matter stayed where it was. So a wave is a transfer of energy, but not matter. So this brings us to the question, what exactly is a medium? So think about other ways we use the word. What does it mean to have a media center at school? What is social media? What do we mean by the word media? Well, media, or a medium, which is the singular, is any material or field that's connected in such a way that a disturbance can pass through it. So for example, each of these little masses is connected to its neighbor. If it wasn't connected to its neighbor, then when the disturbance got to one point, for example, right here, if this guy couldn't tug on its neighbor, then the disturbance would end right there, and this guy wouldn't move. So these guys have to be connected in such a way that the disturbance can pass through them. Okay? So a media is a material or a field that is connected that a disturbance can pass through. Now, if you think about the entire way our information system works, something happens at school, the TV and the newspaper show up. We call those the media. For example, to a football game, the media pass allows a person to come and report or take pictures. And so they are part of the system through which information passes. They then go back to their station, they broadcast the signal on the TV, and everybody can see the New Pal cross country team running across the finish line in the middle of the football game. So the media is what we call the connected system that allows information to pass. And so the media center used to be where you would go if you wanted to figure out some information. Nowadays we just go to Google, but that's how we use the word media. Okay, so media is anything through which a disturbance or information or energy can pass without transmitting matter. All right, now, there's two types of waves. One type is called a pulse wave. So this is an example of a pulse wave. A pulse wave just happens once. The disturbance propagates along the medium, and it's over. I can send another pulse wave, and I can make it go fast. And I can send another pulse wave, but pulse waves are individual waves that don't repeat. Okay? The other kind of wave that we're going to care about and we're going to look at is a periodic wave. So a periodic wave is a wave that is created, or a disturbance that is created by a simple harmonic oscillator. So imagine I have a wheel connected to this rod, and it causes the end of my spring to go up and down, up and down. So this is a simple harmonic oscillator, and you can see that, I'll slow this down so it's in slow motion. You can see that the wave is propagating out, and it keeps coming. This thing keeps making new waves. So that's what we call a periodic wave. They're created by repetitive events, which is generally harmonic oscillators. And by the way, our vocal cords are harmonic oscillators. They produce sound waves. We'll talk about that more later. So this is the kind of wave we're going to study. We're not going to really look at pulse waves. They're very hard to describe mathematically. So we're just going to focus on periodic waves, waves that are created by repetitive events, okay? All right, so there's a couple of different types of waves. The first kind of wave is a transverse wave, and you might want to jot some notes down here, so feel free to pause the video if you want. But a transverse wave is a wave where the disturbance in the media is perpendicular to the direction of the energy propagation. So let me go back to here and try to show you what that means. I think you guys can see that here is a wave and it's traveling to the right. So when this thing makes a wave, the waves travel to the right and they travel off out the window and on forever. So the energy propagation is to the right. But if you look at any piece of the media, so take a look at this ball right here, this green ball. Watch which way it moves. So you can tell this green ball is actually moving up and down, which is in a direction that is perpendicular to the left-right motion of the wave. So we call this a transverse wave. So transverse wave is when the disturbance in the medium is perpendicular to the direction of the energy. Okay? So the media moves up and down while the energy is moving to the left or to the right. That's a transverse wave, and light is a good example of a transverse wave, as is when you shake a slinky. Another kind of wave is a longitudinal wave. So in this case, the disturbance of the media is actually in the same direction as the energy propagation. And I'll show you this in 1 second. There's actually a third kind. You don't really need to know it, but I'm going to show you a torsional wave later on in a video when a bridge collapsed. But this is a rotational wave, so that's not very common. So let's jump back to transverse and longitudinal. Here's an example of a transverse wave. I think if you can see, you can follow my little laser pointer. The wave is moving to the right, but if you put your eye on any one of these dots, you'll see it's actually moving up and down. So the motion of the media is perpendicular to the motion of the wave, which is to the right. That's a transverse wave. Now this is an example of a sound wave. So we can't see the air molecules, but if you could record their position, on the left-hand side here, we have a speaker moving back and forth, sending out waves. And these waves are called compression waves or longitudinal waves. And you can see, like right where the laser pointer is, you can see there's an area of dense waves moving along to the right. Okay? So the media is moving in the same direction. Focus on this little dot right here, and you'll see that little red dot goes to the right and then the left, and then to the right and then to the left. It doesn't move down the pipe. This dot doesn't end up all the way down here. It just moves back and forth, but in the same direction as the wave. And so that is what we call a longitudinal or a compression wave, and that's an example of, and a sound is a good example of that one. Here's another kind of wave. So if you notice, if you put something, an empty bottle on the water, you'll notice as the waves go by, it'll bop up and down, but it also kind of jerks back and forth a little bit. And if you were to very carefully plot its motion, you would notice that it's actually moving in a circle. So that's called a circular wave. And a circular wave is a combination of the media moving up and down. At the same time, it's moving to the right and to the left. So it's a combination of transverse and longitudinal waves, and that's really complicated, so we're just going to focus on the other two, but that's another kind of wave. All right, so when we talk about waves, we talk about 4 parameters. We talk about the period and the frequency, which you are used to. We talk about the amplitude, which is how big the disturbance is, and we talk about the wavelength. Okay, so let me go back to my simulator here and try to explain those. So the amplitude is how far this is moved from equilibrium. So if I were to pause this and actually make it completely stop, so here we go, let's see, I'm going to make the amplitude 0. Okay, so this thing is not moving up and down. We are not displacing this from equilibrium. Okay, so if I make the amplitude small, you can see there are small displacements from equilibrium. Okay, so the amplitude is how far this thing moves from equilibrium. So if you imagine any spot on here, so this green dot, how far does it move from that center line? That's the amplitude. Okay, and if I crank up the amplitude, we can make it move really far. So that's a large amplitude, and that's a small amplitude. Okay? The second thing we talk about is the frequency, and the frequency is how many waves pass by every second. So if I were to get a stopwatch, for example, and I'll start my stopwatch, In 1 second, I could say, if I think about this point right here by the window, how many waves? Here comes one wave, here comes another wave. There are 2 waves coming by every second, right here where my pointer is. So the frequency is the number of waves that pass by every second. It's also the number of waves that are created every second. If we have a high frequency, we are making lots of waves every second. And if we have a small frequency, we're making very few waves per second. In fact, this is only making half a wave every second. Okay? The next thing we want to look at is the period. The period is the time it takes for one single wave to go by. So if I look at some spot, like maybe right here on the edge of the picture frame, and there goes a wave, there comes a wave. So if I go from the top of one wave to the top of the next wave, that time is the period. You can also see that these waves are traveling down the string with a velocity. We're going to talk about the velocity in a minute. The last thing I want to talk about is the wavelength. So the wavelength is the distance in space from the top of one wave to the top of the next wave. How far these are spread apart is called the wavelength. Okay? So here's a slide that kind of diagrams what we have. When we have a wave that is traveling to the right, the amplitude is the distance from the maximum to the point of equilibrium. This is the point of equilibrium is where it would be if there was no disturbance. So this distance here is the amplitude, okay? And it's the exact same as the distance from here to here. That's the amplitude. The wavelength is the distance between the 2 waves, how far apart they are. And both the wavelength and the amplitude are measured in meters. The period, of course, is the time it takes one wave to go by, and the frequency will be the number of waves that go by in 1 second. So those are the 4 parameters we use to describe waves. Now, the wavelength is a new one, and we're going to use a Greek letter to represent wavelength. So here's a chart of the Greek alphabet. Maybe you've seen some of these before, especially now in the age of COVID. Here is delta. We use that to mean change, and you guys know there's a variant of the COVID-19 virus called the Delta variant. Omicron is another one. We don't use it very often because it looks exactly like our O. So, except to name viruses, we don't use it in physics very much. You've seen some of these other ones. You've seen pi probably, and theta you use in geometry. Well, this one right here, lambda, it's kind of like a Y, but it's upside down. This is the letter we are going to use to represent wavelength. So the variable we're going to use when we're using equations for wavelength is going to be this lambda thing. All right, so let's talk about the speed of the wave. You can actually go to this simulator if you want, and you can play with it. I'll give you a link in a minute. But one of the things you can do is you can measure the speed of the wave. You can get yourself a ruler, and you can measure how long it takes this wave to go all the way to the window, which is 7 centimeters away. And the thing you will notice is that if you have little waves or big waves, so we could make big waves. So you have little waves or big waves. You could have high frequency waves, or you could have low frequency waves. But the speed of the wave, how fast this wave moves to the right, doesn't depend on the amplitude or the frequency. Okay? So what does it depend on? Well, the wave speed doesn't depend on the frequency or the amplitude. What it depends on is how tightly the media is connected. So in the case of a piano string, that's the tension. In the case of a spring, it's the spring constant. In the case of sound waves, it's how tightly the air molecules are connected so that one air molecule can smack into another air molecule. So the wave speed only depends on the medium. And we can calculate the speed of the wave. The speed of the wave is the distance it goes divided by the time. The distance it goes is the wavelength. That's this lambda thing. The time it takes one wave to go by is the period. So the wavelength divided by the period is going to tell us the velocity of the wave. We usually rewrite it like this. We take the wavelength times 1 over the period. That's exactly the same as this. And 1 over the period, of course, is the frequency. So the wavelength times the frequency is how we find the velocity of the wave. All right, and so that gives us our wave equation, and this is the equation we're going to use to solve some little problems today. Okay, so this is in your toolbox. Take a look and make sure you know where it is. The velocity of a wave equals the wavelength times the frequency, and remember this is the Greek letter lambda, and it's kind of an upside down y. All right. Coupled with that equation, you already know the period is 1 over the frequency, and of course the frequency is 1 over the period. So when you try to find the frequency, you can take 1 over the period and you'll have the frequency, then you can solve the problem. Okay. Now, there are 2 common wave speeds that it's good to know about. The first of all is sound. Sound travels 341 meters per second. It doesn't matter whether you make a high frequency noise or a low frequency noise. The speed of the sound just depends on the air, and it's 341 meters every second. Okay? So that turns out to be about 1/5 of a mile every second. So it takes sound about 5 seconds to go a mile, which is pretty darn fast, but not instantaneously. The other common wave is an electromagnetic wave, so we use EM here. So electromagnetic waves are the waves that are created when atoms vibrate. So electromagnetic waves include light, radio waves, cell phone waves, X-rays, microwaves, radar, all of those are electromagnetic waves. And they all go 300 million meters per second. These waves move extremely fast. They can go all the way around the Earth 7 times in 1 second. So they move extremely fast. So it's a fun fact to know that this number here is so important in physics, it gets its own letter. We don't use C for anything else in physics. You may have noticed we have not used it. The chemists use it for heat capacity, but in physics, we reserve the letter C by itself for the speed of light, or we call it the speed of light. It's the speed of electromagnetic waves. So if you see lightning, then here's an easy rule of thumb. The light gets to you almost instantly, but the thunder, the sound, takes 5 seconds to go a mile. So if you see lightning and 5 seconds later you hear the thunder, then you know the storm is 1 mile away. If you see lightning and you hear the thunder 10 seconds later, you know the storm is 2 miles away. If you see lightning and you hear thunder right away, like less than a second, then you know the storm is right on top of you. You better find someplace low and duck, because it is less than 1/5 of a mile. All right. We're going to use metrics prefixes when we solve these problems. This is in your toolbox also. It's near the front. You might want to locate it. We're going to use these. So when you see a G, M, K, little m, Greek letter mu, or an N in front of a measurement, like in front of hertz, that means it's a metrics prefix. Okay? So here's 2 examples that you're going to solve in your problems. Bluetooth communications happen between your phone and your headphones, for example. They send out electromagnetic waves, and those waves are 2.45 GHz. So this is a gigahertz. See the hertz? You know hertz? The G in front of it means gigahertz. So the question is, what is this frequency in hertz? So don't make this problem harder than it is. I'm just trying to see if you know what giga means. So you look up in your table of metrics prefixes. Giga means 10 to the 9th. So 2.45 gigahertz simply means 2.45 times 10 to the 9th hertz. All right? That's the frequency of the waves that are created by your phone when it's communicating with other Bluetooth devices. So it's actually taking atoms or electrons and it's shaking them up and down 2.45 times 10 to the 9th. So more than 2 billion times every second, those electrons are shaking up and down in a little antenna, and that sends out a wave which goes to your headphones, and it carries the signal for your sound, your music or whatever. All right, here's another example. Suppose I have a radio station, 90.1 megahertz. The M is a metrics prefix again, and so when you tune your radio on your car, you're tuning it to the frequency of the station you want to pick up. So that's WFYI, my favorite station. And in a big old antenna up there by St. Vincent's Hospital, electrons are wiggling up and down, and that's sending out a wave. Okay? What we know is the velocity of electromagnetic waves is 3.0 times 10 to the 8th. we know the frequency is 90.1 megahertz, which is 90.1 times 10 to the 6th hertz. Remember, mega means 10 to the 6th. So I know the velocity and I know the frequency. So I can find the period. The period, of course, is simply 1 over the frequency. So if I take 1 divided by the frequency, I'll get 1.11 times 10 to the negative 8th. So that's how long it takes one wave to go past my antenna on my car. I can also find the wavelength. These waves that are spreading out, what is the length of the wave? What is the distance from the peak of one wave to the peak of the next wave? So since the velocity equals the wavelength times the frequency, and I want the wavelength, I can divide both sides by the frequency. So the velocity divided by the frequency will tell me the wavelength. And that turns out to be 3.33 meters. That's the distance between the top of one wave and the top of the next wave. So you're just going to solve some simple little problems. You don't need to show your work. You're just going to do the calculations. You're going to need to remember your metrics prefixes and use those in your toolbox. You're going to use this equation. The period is 1 over the frequency, and the frequency is 1 over the period. And you're going to use the wave equation, which is that the velocity equals the wavelength times the frequency, and you're going to calculate one of those three things. Okay? So you've got some problems to solve. So get going on that. We're going to use this as we move on into sound in the next lesson when we're hopefully back at school.